Hi, grade 12s. Today we're going to look at graphs of derivative functions, or the graphs of a function's derivative, if that makes sense. All right, so let's see what happens. We've actually done this before, so the first thing we're going to look at is we're going to look at the graph of y is equal to 2x cubed minus 3x squared minus 12. You'll notice it's got nice x-intercepts, nice turning points, and all is well. We've got a turning point there of minus 1 and 7, and then we've got a turning point there of 2 and minus 20. So, and we've got a point of inflection there at a half and minus 6.6 and 6.5, minus 6.5. All right. Now, and then on the bottom there, I've got the graph of the derivative of that. So in other words, the graph of 6x squared minus 6x minus 12. Let's quickly just look at let's just compare these two graphs again and see what happens. So the first thing that we will notice is that the x value of the turning point, right, x values of the turning point is exactly the same as the x values of the intercepts. So that was one of the first observations, remember, that we did. So the x value of the turning point of the original function is equal to the x-intercept of the derivative function. Why is that the case? In this graph, we've got, that is the graph of f of x, right? So y is equal to f of x. And this is then the graph y is equal to f prime x, the derivative of f of x. Okay, so how would you normally find the x-intercepts, right? To find the x-intercepts of this parabola, you would say, well, let's make y 0, right? I mean, that's where y is equal to 0. In other words, what you're going to do is you're going to say, well, it's that derivative that's equal to 0. Ooh, and check what happens. How do you normally find the stationary point? Well, that is when the derivative is equal to 0. Isn't that just too beautiful? So there's the link between the x values. The x-intercepts of the derivative graph is equal to the x stationary points of the original function. Okay. The next thing we're going to look at is the point of inflection, right? So what happens with the x values, or the x value of the point of inflection, that is then going to equal to the x value of the turning point. And why is that the case again? How would we normally find the point of inflection, right? We would say it is the x value when the second derivative is equal to 0, right? Good. But then how would we find the turning point of a parabola for this part here? Remember, this is the graph again, y is equal to the derivative of f of x. And how would you find the stationary point, or the turning point? You would say, well, we would find dy over dx, we would find the derivative and equal that to 0, right? So in other words, so if y is equal to f prime x, what is the derivative of that? Well, it's going to be the second derivative then. It's the derivative of this function, but this is already a derivative, so it's the second derivative and you equal that to 0. And of course, you see those two are the same. Oh, so beautiful. Next up, we're going to look at where the graphs are increasing, where the original graph is increasing and decreasing. So the graph is increasing from left to right, of course, all the way there, up to that x value of the turning point, for all those x values. In other words, so increasing, so for x is less than minus 1, right? All those x values, the graph is increasing. And then it decreases, and then it increases again right after that turning point there. So in other words, then it will increase again after 2. Okay, so for all those values, that says increasing. All right, and then the slope will be negative. The derivative will be negative. The slope will be negative. Where? Well, between those two x values of those stationary points, right? In other words, between between minus 1 and 2. For all those real values, the slope would be negative. Okay, but remember, this is the graph of what again? This is the graph of f of x, right? Y is equal to f of x. This is again the graph of y is equal to f prime, the derivative of f of x. So what does this now mean? So okay, so we said the graph is f prime x is greater than 0 for x is less than -1, x is greater than 2. So what we now see is, what happens here? All the values less than -1. That is where y is positive. So there you've got positive y values, right? And there all the x values greater than 2 will also have positive y values. You with me? And then we've got negative y values between -1 and 2. So there we've got all those x values will give you negative y values. Okay, and what's y in this case? Y is not y, y is f prime x. So in other words, the f prime x, when y is positive for all those x values less than -1 and for all the x values greater than 2. You with me? And then f prime x, y in this case, remember y is that, y would be negative for all the x values between -1 and 2 for all those real values. And do you see they're exactly the same? So f prime x is greater than 0 for x is less than -1, x is greater than 2. And then f prime x is negative for that. So that's also a fine link to make. So in other words, the graph would increase, right? The same x values for where the derivative graph is above the x-axis, right? It increases where the derivative graph is above the x-axis. The graph, the original function, will decrease for those same x values where the derivative graph is below the x-axis. So there's another conclusion we can make. Next, we're going to look at the concavity aspect, concave down. So this original function will concave down for all the x values, of course, less than the point of inflection there, to the blue part. So there it concaves down. It's got a maximum turning point. In other words, any x value here less than, what was it, a half, right? Any x value less than that x value of the point of inflection, your second derivative, if you substitute it into the second derivative, you're going to get a negative answer. So in other words, if you substitute -1 into the second derivative, you're going to get a negative answer. That's indication of its concaves down. All right. What happens at the point of inflection? It neither concaves up or nor down, or well, some people believe it does both of those, but I'm not convinced. But so what happens there is at the point of inflection, I think it neither concaves up nor down, and so that is just the 0. That rate of change is 0 there of the rate of change, right? And then there it concaves up again. So in other words, what happens there is you're going to get any x value greater than that point x value of the point of inflection. If you substitute into the second derivative, you're going to get a positive answer. So if I would ask you, is this turning point a maximum or minimum turning point? Can you explain? What you can do is you can just work out the second derivative, substitute that x value of the turning point into it. If that x value, if the second derivative of that x then is positive, it concaves up, so therefore it will be a minimum turning point. If you substitute that x value of the turning point, or any part of that, into the second derivative, and that answer is negative, it will concave downwards, so therefore it's a maximum turning point. Hopefully that makes sense. And then just to compare that quickly, so now this is the red graph. There's the second derivative is greater than 0, and the blue graph, blue part there is the second derivative is less than 0. So and just with the derivative graph, what does that mean there? Well, that is where the slope there, it's got a positive slope, right? And it's got a negative slope up to that x value of the turning point at a half. And you see that's of course where it changes. So so this is where the derivative of the function, remember this is y is equal to f prime x. This is where the slope, the derivative of that derivative, is the second derivative, is negative, and that of course is where the derivative of the derivative, the second derivative, is positive, and they share the same x values. In other words, if you just make that link, they share those same x values. Hopefully this is useful. Right, and then in your textbook, there's that page 121 and 122. It just goes through exactly what I've just said. So if you've got a function, so this is y, that is y is equal to f of x, right? That is y is equal to f prime x. Then the x value of the original function's stationary point will be the same as the x-intercept of the derivative function. Same story there, right? So in other words, we're just going to work backwards now. In other words, what I'm going to do is I'm going to give you this, and you, in other words, can give me some sort of that. So the same story here. We've got a stationary point of a cubic. This is a positive cubic, right? In this case, A will be positive. It starts low and it ends high. So, and this one ends high and it finishes low. So this is where A is negative. And the leading coefficient. So the stationary point of your original function will be the same as the x-intercept of the derivative function. Okay, hopefully that makes sense. So, and also when it's a negative function, it's the same story, okay? But of course, then what just happens is this part is, that part is where if the slope, so where f prime x, not the slope, sorry, where the y values are positive. And if you compare that to the top part, that is of course where the slope, the same x values where the graph slope will be positive. Do you see that they share those x values? Positive slope, positive y values, because the slope is the derivative of the function, right? And yeah, and then of course we've got a negative slope, alright? So that is when f prime x is less than 0, alright? And that is of course where, but that this is y is equal to f prime x, and that is where it's below the x-axis. So hopefully you're seeing those links. That's the same story. So it's a negative slope and it's below. That's also where f prime x is less than 0. Okay, so like I said, we're just going to give you that now, and we're going to move on to there. Okay, so let's look at question B on exercise 11 on page 124 in your textbook. So this is when the graph of y is equal to f prime x is given to you. Okay, so they give you the derivative graph now, and now they ask you normally questions in terms of f, of the original function. Okay, so the derivative graph now is a parabola. That means the original function was a cubic, right? And it would have been a positive cubic. So f of x, that f graph would have looked something like that, right? And what do we know? What's the relationship again? So the x-intercepts of your derivative graphs is the x values of those intercepts, of course. The x-intercepts of the derivative graph is the same as the x values of the stationary points of your original function. Remember that, okay? We just did it now. So let's answer these questions quickly. And sorry, the last bit. The stationary point of this derivative function then is the point of inflection. It's the same x value as the point of inflection of the original function. Okay, let's give it a go. So this is not the easiest thing. So let's just go step by step through it, and yeah, let me know if you've got questions. So what's the gradient? What is the gradient of the tangent to f at x is equal to 0? Okay, so we just said this is the graph y is equal to f prime x, right? It's the derivative graph. So y is equal to f prime x. Okay, so in other words, this point here, what is the coordinate of that point? You would normally say it is, well, a coordinate is xy, right? So what is the x value there? Is 0. And what is the y value? It's 9. But what is, this is the function, it's not just a normal f of x. This is a what? This is a f prime x function. So that would mean it is x. You would normally say it is x, x and y coordinate is then x and f of x, right? That's what you would normally do. But in this case, it is what is y now? Y is not f of x. No, it's not. Y is equal to f prime x. So therefore it is x and f prime x. Does that make sense? So therefore, what do we know now? we know then that, well, x is 0, and we also then know that f prime x is equal to 9, right? Those two must be the same. F prime x is equal to 9. Y is now not fx, y is f prime x. Okay, and what does that mean? Well, f prime x, that the derivative of f of x is the slope, right? So the slope, the gradient, is equal to 9. And what did I ask you? What is the gradient of the tangent to f at x is equal to 0? And that's exactly it. In the second question, write down the x-coordinates of the stationary points of f. What did we say the link was again? The x-intercepts of your derivative function has got the same x values as has got the same x values of the stationary points, right? The x values are the critical part there. Okay, so in other words, what we know is you have those coordinates, so it's 1 0 and it is 3 0. Okay, and remember it's x and y. So that would mean, okay, what is y in this case? Y is equal to f prime x, right? So therefore it is, well, it's going to be 1, and it is f prime of 1 is then equal to 0, right? We substitute. You would normally do that with f of x, but this is not f of x, it's f prime x. And then in the similar sense, we've got 3, and then we would normally say, well, it is f of 3, but in this case it is f prime of 3, the derivative of f of x of 3, and that must be equal to 0. In other words, what we know is, we know that the derivative of f at 1 is equal to 0, and we know that the derivative of f at 3 is equal to 0. Okay, so that's important. So what does that mean? So write down the x-coordinates of, write down the x-coordinates of the stationary points. Just simply what that means, of course, is that the x values of the stationary points, so this is when we, in other words, f of x is equal to 0. Where is f of x equal to 0? It's going to be 0 at, well, at 1. And f of x is going to, the derivative of f of x is equal to 0. That's how we normally find the stationary points, right? Where is it also equal to 0? Well, it's going to be 0 at 3 when x is equal to 3. So that's what that means. Next up, write down the coordinate of the point of inflection, and again, let's have a look at that. So what we have here is we've got the stationary point of the derivative function. So in other words, we know it is, so it's 2n minus 3. It's a turning point, right, of the derivative function. Okay, so that means, well, that is x, and that is f prime x, right? Good. And how would you normally find the derivative? You would say, well, that is when, let's see, you've got f of x is equal to blah, 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 blah. What we normally do, you would say that is where the derivative, second derivative, sorry, for point of inflection, the second derivative is equal to 0. It is those specific x values. Okay, but what is the, how would you work out the turning point of a parabola? You would say, well, that is when in my function, so for example it's y is equal to what, we're finding the derivative, and that is where that derivative is equal to 0. We find the x value where the derivative is equal to 0. Okay, but now the issue is our function is already in derivative form, so that's our normal y. So what you're now going to do is you're going to find the derivative of that part, okay, which means that is the second derivative, and that of course you're going to let equal to 0. Okay, good. And what does that mean then? What is the x value of the stationary point? That x value is going to equal to 2. So therefore, what is the x value of the point of inflection going to be? Well, that is going to be at 2. Remember, the turning point's x value of the derivative function is the same as the x value of the point of inflection of the original function. Okay, so this question is a bit more interesting. So we're asking, what is the gradient of the tangent to f at its point of inflection? All right, so let's look at that point of inflection again. So, well, first of all, let's look at the stationary point in total, right? So the stationary point of this is 2, -3, right? So, which means it is 2 and f prime of 2, right? Does that make sense? So again, normally you have x and y, and then which actually just means in a coordinate, and that means x and f of x, right? But what is y in this case? If that's x and y is not y is in this case because it's a derivative function. It's f prime x. So therefore it is f prime 2, the derivative of f at 2. Okay? Hopefully that makes sense. So what does that mean? So that means that f prime 2 is equal to negative 3, alright? So what does that mean? That means, okay, so how would we normally find the tangent? Okay, so you would say y is equal to mx plus by c, and how do I find m? We would say, well, it's where it's the derivative of the function at the x value of the point of tangency, right? Good. Hopefully this comes back to you. So therefore, okay, that's m. Okay, and in other words, we know what that is, because what is the derivative of this function is f prime x, okay? So that's about there, so f prime x, and it's f prime at 2, and that answer is minus 3. That would mean the gradient, so the gradient of the tangent at x is equal to 2, which is the same as the x value of the point of tangency, is equal to, what did we say? Negative 3. Alright. Alright, so you'll be able to do the next one, hopefully. So for which values of x is f, the original function, increasing? For the original function to increase, okay, so increasing, remember, means where the slope is positive. And for something, for a function to decrease, that means the slope must be negative. So for which values of x is the slope, is it increasing? So where's the derivative, where's f of f prime x, in other words, greater than 0? Oh, and remember, this is f prime x, and where is it greater than 0? It's greater than 0 there, and it's greater than 0 there, alright? So let's make this red, and where's it decreasing? Where's f prime x? Negative. Remember, that means now y is negative, because this is the function f prime x. So where is y negative there? It's negative there, between minus 1 and 3. So therefore, where is it increasing for the first part? It's increasing for all the values less than 1, or all the values greater than 3, right? And where is it decreasing? It's decreasing, in other words, between 1 and 3, all those real values. The next question is beautiful. So they ask you if f is concaving up or down at specific x values. Let's just quickly go through that again. Concave up is when the second derivative, okay, when the function's original function's second derivative is greater than 0. For that part, you get a concave up. Right, remember, it changes the point of inflection. Because at the point of inflection, the second derivative is equal to 0. And then concave down is when the second derivative is less than 0. Okay, so but let's look at this. So this is now the graph of f prime x, right? So it's the y is now equal to, okay, so he's saying it again, but y is equal to f prime x, okay? And what would that mean? So in other words, if f prime x in this context would mean the slope, right? So you need to find the derivative of this graph for it to be the second derivative, because the original graph, so this graph here is a derivative graph. Ooh, I'm not sure I'm saying that right. So here we go. This is, so this is y is equal to f prime x, right? Good. So if I would, what would f double prime x, what will be the second derivative in terms of this graph? It would be its slope, because if you're finding the derivative of a function, you're finding the slope. Hopefully that makes sense to you. So in other words, there's the change in slope, of course, is at the stationary point, and then there's a slope. Okay, so the derivative of that function, the function, remember, that's been drawn there, that parabola, is f prime x. The derivative of that would be f double prime x. So what's been drawn there is the derivative of f of x, so the slope of it will be the second derivative of f of x. Okay, so the green part there is where the second derivative is greater than 0, the derivative of that function, and that function is the derivative, right? And then the green part there is when the second derivative is less than 0, it's decreasing. All right, so remember that parabola is f prime x, so that is where that slope, so in other words, the derivative of that, so it's f double prime x, is less than 0. Okay, and then they ask you, so does the graph concave up or down at x is equal to 1? So at x is equal to 1 is right there. In other words, what would happen then? If you would substitute 1 into the second derivative, you're going to get a negative answer. So at x is equal to 1, you're going to get the graph there so it's the second derivative where that's less than 0. So in other words, less than 0, it concaves down. Okay, good. And then hopefully that makes sense. And then at x is equal to 4, let's have another color just quickly. No, come on, you. And no, not that one. That one. So at x is equal to 4, where's x equals to 4? It's like there somewhere, right? So at x is equal to 4, that's the green part of the graph. What's the green part of the graph? Ooh, that's where the second derivative is. The slope of that graph, the second derivative, is greater than 0. In other words, what does that mean? It has a smiley face, therefore that will concave upwards. Too good. Right, and then the last part we need to draw just a rough sketch of the original function, that f of x. Okay, so what do we do there? They gave you a very important point there, so that f of 0 is 0. That means that is the point 0, 0, right? X is 0, y is 0. So in other words, that the original function will go through the x-axis. So what do we know? So the x values of the original graph stationary points is equal to the x-intercepts of the derivative function. In other words, these are just dotted lines, right? They're not asymptotes, please not. So somewhere on those dotted lines, there's going to at 1 and at 3, right? These the stationary points are going to lie on that. Okay, good. That's the first part. Second part is the point of inflection is going to be at 2, right? So somewhere halfway between those, of course, is a point of inflection, so that is at 2. What else do we know? That the graph will increase where the graph would increase and decrease, and we just looked at it now. So this part here, so that green part, so that is when the second derivative would be greater than less than 0. Less than 0. Less than 0. That's where the slope of that function is going down. So in other words, in this part, the original graph will concave downwards, and then the second derivative greater than 0. So the slope of that second derivative greater than 0 is then the concave upwards. So that it's that part there. In other words, all the values greater than 2. So it's going to have a concave up and down. Okay, to separate the concave up or down. Okay, so in other words, what we've got is we don't know the y values of those stationary points. It doesn't really bother us at this stage. So in other words, we know the function is going to go up, right? Somewhere on this, at x is equal to 1, it's going to turn. Okay, we don't know where that point is, right? So that point can be there or it can be down there. Right, so we don't know. It's going to turn. Somewhere there is going to be a point of inflection. Somewhere at x is equal to 3, it's going to turn again, and it's going to land up there. Right. Let's look at the following one. So this is not in your textbook. I saw this and I thought if the previous one was a bit hectic for you, let's just build up on something a bit easier, right? And just to ground those concepts. And then after this, I'll do something a bit on steroids again. So the graph represents a cubic function y is equal to f of x. So you will be delighted. This is the original function, and it's a cubic. So all is well. All is well. So here we go. So and then they told you that a, b, and c. So a, b, and c. They are some x-intercepts. D and e are the x values of the stationary. D and E are the x values of the turning points, and then h is the point of inflection, x value of the point of inflection of the curve. Okay, and write down in terms of the given constants the values for which, let's do the first one, for which f prime x is greater than 0. What does that mean? That means this is the graph of y is equal to f of x. F prime x, which just means the slope of that, right? Where's the slope greater than 0? In other words, where's the slope positive? The slope will be positive only there, right? And what will only there be? It's between d and e. So it's, remember they ask you for the x values. So it's all the x values between d and e. X is greater than d and x is less than e. Alright, so all those real values. So question B then, for which values of x will f prime x be equal to 0? So what would that mean? That means where's the slope of this 0? Where's the slope of this 0? That means it's the x values of the turning points they're referring to there now. So therefore that will be at x is equal to d or at x is equal to e. Question C. For which x values will the second derivative of f of x be equal to 0? That, of course, is the x value of the point of inflection. The point of inflection is at h. Okay, good. So the point of inflection is at h. So that will be x is equal to h. For which values of x will the graph concave up? Right, concave upwards. Just erase this a bit. Concave upwards would mean, where is it making that? It looks like a smiley face parabola, right? It concaves. Remember, the concavity would change after if you flossed or when you find the second derivative and equal it to 0. So here we go. So that is where it concaves upwards. So that means that the second derivative is greater than 0. So for which x values, that is all the x values less than that x value of the point of inflection, and that would be at h. Question E, for which x values will the f prime x be equal to 0? Oh, Crisis, what does that mean? So that means where's the derivative equal to 0 and where f double prime x is less than 0. So f double prime x less than 0, that means it's a sad face parabola, like some of your faces when you see me. So, and then, so in other words, they're asking you which stationary point, okay, will be where there's a negative concavity, okay, when concaves downwards. Which stationary point? So that, of course, would be at at x is equal to e. It's this dude. Let's see if that makes sense again. So f prime x is equal to 0 is the stationary point, so it's either going to be at x is equal to d or x is equal to e, but at if they ask you for, it must also agree with the second derivative must be less than 0. Second derivative less than 0, that means it must concave downwards, right? Because the purpley part is where it concaves upwards. And there we go. Here it is. So there we go. Okay, so the next one they ask you, so where's y, f of x less than 0? That means where's y negative? Okay, so first of all, let's check where's y negative is all those x values, right? So all those x values where y is negative, and then there's y negative again. Very negative. Again, like you. So, and then they also ask you, where's the derivative? Where's f prime x? Where's the derivative of f of x? Where's that positive? So for which x values will there be negative y values, all right? But it must have a positive slope. Okay, so let's go. So in other words, all the negative slopes are out. So let's go. That's a negative slope. So all the values less than d, they're out. Let's not mess this up. Okay. Then we've got a positive slope. Positive slope. There we go. And then we've got a negative slope again. Good. So we want to know all the x values where there's a negative slope, the red slope, and where I want all the x values where there's a blue slope, a positive slope, and where there's negative y values. In other words, where's the blue part of the graph under the x-axis? And where would that be? Of course, that would be here. Let's do a different color. So that part there. All those x values, what happens there? They're below the x-axis, right? So that means fx is less than 0, and it means that it's got a positive slope. It goes uphill. So let's check what happens here, right? So from here, we've got fx is greater than 0, not less than 0, greater than 0. It's a positive y values, but it's got a negative slope, so that's just totally wrong. So we want negative y values and a positive slope. Okay, so that's the issue. Okay, so there we've got negative y values, but we've got a negative slope. Ooh, yeah, we've got negative y values and a positive slope. That's what we want. And then we've got a positive slope, but positive y values. And then we've got negative slope and positive y values. Okay, so 1 is correct. We want a no, we don't want a negative slope. What am I talking about? So the only one that will satisfy this is this area here, right? Between D and H. No, D and B. Sorry, my glasses. So here we go. So it's all those values between D and B. Okay, so all those will have, it's got negative y values and it's got a positive slope. So great, Charles, how's it going with you, eh? You doing well sitting there? Yeah. Getting as much response from you as I normally get in class. Yeah. Only questions I'm not getting is, can we have a break and can I go to the bathroom? So it's been quite an adjustment, but yeah. Okay, let's look at question G. So for which values or which way would f of x, well, let me just erase this quickly. It looks like a party pack. Okay, so f of x is greater than 0. Ooh, what does that mean? That means y must now be above the x-axis, right? So y must be positive, very positive, and positive. There's y is very positive. Okay, good. And the second part is it must also have a positive slope. Okay, so where will it have a positive slope? It will have a positive slope here. Right, and that's the only part where it will have a positive slope. So we want to know where's the green and the blue part. Yeah, where is it above? Where's y positive? Where's the graph above the x-axis? And where does it have a positive slope? And it will be both of those between. Not all at once, please. So between b and e. Yes, all those real values. Okay, so let's look at one of these. Once you've been given the derivative function, I know that scares some of you. Let's see. So here we go. So you've been given y is equal to f prime x, and they ask, of course, all of these questions in terms of f of x, which is not drawn there. And grade 12s, I warn you, if you're going to, if I put a question like this in June or in prelim, where there's a strong likelihood I will. And if you're going to call me to the examiners and they're like, yeah, there's a mistake there because f of x is not drawn, I will, oh my goodness, I will think of something horrible to say to you. So please don't do that. Okay, let's go for it. So determine the values of x which the function f is increasing. F is not drawn there, but where would f be increasing? So if I've got a normal f of x function, right, it will increase, of course. That's when the gradient is positive or negative. Okay, so increase means the gradient is positive, decrease where the gradient is negative. So we want to know where's the gradient positive for it to increase. So in other words, in this case, so now where's f prime x greater than 0? Now this is f prime x. All the y values here are, they are actually f prime x. So where's f prime x positive? Where is it above the x-axis, in other words? It's above the x-axis all the way there, right? So in other words, which values will be increasing? So between -4 and 2, all those real values. Right, question B. The x-coordinates of the stationary points of f. So x-coordinates of the stationary points of f. So let's just quickly look at those relationships again. So the x-intercepts of the derivative function has got the same x values of the stationary points of the original function. And then the turning point of the derivative function, that x value of the turning point of the original of the derivative function, is got the same x value of the point of inflection of the derivative of the original function. Let's say that again. The x value of the stationary point of the derivative function has got the same x value of the point of inflection of the original function. Okay. I'm not writing all these things down. I do think it's a very important part. You need to be able to say that and to make a total hash out of it like I do. So the x-coordinates of the stationary points of f. The stationary points of f is when f of f prime x, the derivative of f of x, is equal to 0. Okay, so where is the derivative of f of x equal to 0? The derivative of f of x again is this function. Where is the y equal to 0 here? Well, there we go, and there we go. So where is it equal to 0 at? Minus 4, and at x is equal to 2. There's the derivatives equal to 0. Okay, let's go for it. Next one, C. The x-coordinate of the point of inflection of the graph of f of x. That, of course, will have the same x value of the stationary point. I just said that, no. So that will be at x is equal to minus 1. Okay, the x value of the stationary point of the derivative function is got the same x value of the point of inflection of the original function. Okay, so question D. The values of x for which the function will, of f, the original function, will concave down. Okay, so the only thing we need to consider here really is just to check the slope of the derivative function. Don't overcomplicate this. Okay, so I love parabolas. What goes up, well, hopefully will come down. So here we go. So there's the two different slopes. So the blue part there is where the slope is positive, okay? In other words, and normally we would say where the derivative of the function is positive, but the function now is f prime x, so it's the derivative of that, so it's the second derivative is positive. And here what we've got is we've got the second derivative, in other words, the derivative of the function has got a derivative, is negative. Yes. And what does that mean? Well, remember, from concave upwards, it means it looks like z, and that means the second derivative is greater than 0. Concave down, would mean, so that means like that, and then the second derivative is negative. Where's my second derivative negative there? Where does that, what's happening here? So where is it negative? It's negative. Where does it change? At the stationary point there, of course. So where's my second derivative negative? At greater than minus 1. So greater than minus 1, it will my function will concave down, my original function, and what is this? So and where does it concave upwards? At all the values less than minus 1. What did they ask you again? Where would it concave down? So it's that dude. Okay. Last question. Question E. Draw a sketch graph of the original of y is equal to f of x, y is equal to f prime x, and y is equal to f double prime x. Showing clearly the x-coordinates of the point of the turning points of the graph, given that, and they tell you again that how, my greatness, how that the graph is going through the origin. So in other words, f of 0 is equal to 0. Okay. So let's go for it. Let's just draw a graph of the derivative here. What do we know? That somewhere at minus 4, at x is equal to minus 4, there's going to be a stationary point. And somewhere at 2, somewhere there's going to be a stationary point. Okay, good. And what else? The point of inflection is somewhere then, well, let's just write these numbers in. Why didn't I write that? And at minus 1, so somewhere at minus 1, there's going to be a point of inflection, right? So for example, we say the point of inflection is there. Okay, and yeah, that's it. And then you just draw it. It's a negative parabola. It means it's a negative cubic graph. So how would that work? So let's go for it. So you just select your stationary point somewhere there. And so it must start going down, it must turn somewhere, point of inflection, and then it must turn again. Just a negative cubic, right? And then just to link it to the top one, so the blue part there, all the values less than 1 is where it will concave upwards, all right? So do you see that dude is going up, So the second derivative is greater than 0, and then of course that also just means that's where the second derivative is greater than 0. You're going to find a minimum turning point, and then that last part there is where the second derivative is less than 0, yeah, and you're going to find a maximum turning point.